Alright, in this example we're going to look at some one-sided limits using the technology that we have. So we're going to find the limit as x approaches 3 from the right of x squared minus 4 over x squared minus 5x plus 6, and we're going to find the limit as x goes to 3 from the left of x squared minus 4 over x squared minus 5x plus 6. These are limits that approach infinity, and I'm going to make a slightly bigger table so that we can find both the left-hand and right-hand limits at the same time here in our table. I'm going to make 7 values here. One, 2, 3, 4, 5, 6, 7. Okay. With 3 in the middle. Alright. And now I'm going to go ahead and type my function into my calculator. Ooh. The wrong button there. Type my function into my calculator. So I've got the quantity x squared minus 4 over the quantity x squared minus 5x plus 6. And I'm going to build my table. Now, since I want finite values in my table, I'm going to change this over to auto again. And I'm going to have my table start at 2.997. And now I'll look at my table. And we see these values, negative 1666, 24.99, 49.99. And good old error at 3. And then 5,001, 2,501, and 1667.7. Okay. Now, these values here are the ones that are going to help us determine the limit as x approaches 3 from the left. And these values here, highlighted in yellow, are going to be the ones that help us find the limit as x approaches 3 from the right. So, limit as x approaches 3 from the right is going to be determined by the yellow highlighted values. And what's happening to those as we get closer and closer to 3 from the right? They're becoming larger and larger positive values. That tells me that the limit is approaching positive infinity from the right. And then I'm going to find the limit as it approaches 3 from the left. And to do this, I'm going to use the values that are on the left and see what happens as those x values get closer and closer to 3. And we get larger and larger negative values, which tells me that the limit as x approaches 3 from the left is going to be a negative infinity. Alright? So that's something you should look for when you're looking at a limit as x approaches a particular value. If the numbers are getting to be larger and larger positive values as we approach, that means that we're approaching infinity. If they're approaching a larger and larger negative value, that means we're approaching negative infinity. Okay, on to example 6 and 7 on relative growth rates. You can read through the ideas here on what determines when one function grows faster than the other, or when they grow at the same size, that I'm going to use here. Make sure you understand those. The first one, if the limit as x goes to infinity of the ratio of two functions is infinity, then the function in the numerator grows faster. If the limit as x goes to infinity of the ratio of functions is 0, then the one in the denominator grows faster. And then in the third option, if it's any value between 0 and infinity, that means those two functions grow at the same rate. So that's the quick boiled down chop through of that idea. Let's apply that in example 6 here. Which function grows faster, e to the x or x to the 4th plus 2x cubed? In order to determine that, I'm going to find the limit as x goes to infinity of the ratio of these two functions. And so I'm going to do that numerically. We've got e to the x over quantity x to the 4th plus 2x to the 3rd. And now I'm going to set up my table to ask, because I want to put in bigger and bigger values for my x value. And I'm going to go over to my table, put in 10, 100, 1,000. That really gets me all I need to see. Oh my goodness. If you look at it for 10, the value is 1.8, and then when x is 100, it's 2 times 10 to the 35th power. Holy smokes. So going up by multiples of 10 really made it grow very quickly. We can get a better idea if we slow down our growth in our table here. Even then, it skyrockets pretty fast. So this value is getting to be an extraordinarily large number. So that's growing to infinity. And the conclusion that we draw from that is that the function in the numerator grows faster. And so when we ask which grows faster, it's going to be e to the x in this example. All right, let's look at the last one. Which function grows faster, natural log of x or square root of x? So we'll find the limit of the ratio of these two as x goes to infinity. And so go back to my calculator, change my function in here. Natural log of x over square root of x. And I'll go back to my table, which is still in ask mode. And let's see, 10, let's go to 100, 1,000, 10,000, 100,000. What does it appear that y is getting closer and closer to? Well, let's go to 1,000,000. 10 million. It looks like as x gets bigger and bigger, this limit approaches 0. What does that indicate to us? Well, that indicates to us that the function in the denominator is growing faster. And so, in this example, square root of x grows faster. Alright, that's the end of the video. See you next time in the next lesson.